Hello everybody. So, on behalf of Rajarashmi Institute of Technology, I welcome you all for this online Zoom session. So, I am Anand Nagarajan, so I'll be the moderator for today's session. And today we have with us our guest, Dr. Arun Kannawadi. So, I welcome him for welcome him for this session, and I really thankful for him for accepting our invitation to be part of this session. Thank you, sir.
My pleasure.
And today we are having our final year mechanical engineering student, Mr. Vinod. So he will be interacting with our guest today. So we have a series of question and answers which have been framed with the intention of making the session interesting and inspiring for us. And of course, there will be a 30 minutes question and answer session. At the end of the 30 minutes question and answer session, we can have questions from the audience. So before we begin, I'll just tell about what we are doing now. Actually, this is the second of the series of sessions which we have planned under the tagline, Believe in the Possibilities. So there is a tagline for our Rajarashmi Institute of Technology. So Believe in the Possibilities. So we are curating a series of inspiring stories. So just 2 days back, we had a session so where a surfer due to his passion in surfing, how he helped in transforming his village into a surfing hotspot in India. And after today's session is also an inspiring story in a whole different way. So of course, I'll be starting with the introduction of our speaker. Then I'll be handing over the session to Vinod. And the coming days also, we have a lot of similar inspiring stories by people. For example, we have a para swimmer. So who, in spite of his setback, is still making waves, literally making waves in the ocean and earning a lot of medals. So it's another inspiring story that's going to come tomorrow. And then every day, or at least alternate days, we are having similar stories. So I request all of you to participate in in such events. And so today, without further delay, I will start the session, and I will hand over the session to Vinod. So I'll just give a small introduction about our guest, and I will hand over the session to Vinod. So our guest, he is currently a postdoctoral research associate. So he is a LSST DRP software scientist. Of course, we'll be listening about this from him in detail. At Princeton University in New Jersey, USA. He has also been a postdoctoral researcher in Leiden Observatory in Netherlands. He is an alumni of IIT Madras. So he completed his Bachelor's of Technology in Electrical Engineering from IIT Madras. He has completed his Master of Science in Physics from the Department of Physics in Carnegie Mellon University. And he has completed his Doctorate of Philosophy from Department of Physics, Carnegie Mellon University again. So he is a programmer because in the current, especially with the students, that's something which we can tell that because we have a separate question talking about his passion for programming. So he's a very active GitHub programmer, and so he's programming language Python, C, C++ and all, and he has also helped in creating a software package, open source software package called Galson, which we'll be talking about in detail. He has given a lot of plenary talks all over the world. So, so with this brief introduction, I think I will hand over the session to Vinod.
Okay, I'll start.
So I hand over the session to Vinod now. Thank you.
Well, a very good evening to all the participants of this webinar, and a very good morning to you, sir, Dr. Arun Kannawadi, all the way from the United States of America. And once again, on behalf of our institution, I'd like to convey our gratitude for actually allocating time for this webinar session, even during this time of turmoil. We all know the situation has gone out of hand throughout the world, and especially in the United States of America. So thank you once again, sir. We have an array of questions for which we're expecting your opinions and views today. And I think to start off with the basics, since we're all from an engineering background, I'm sure at some point of our lives we've come across the word astrophysics, but we really have little to no knowledge about this field. So if you could describe as to how astrophysics is as a career, and describe a day in the life of an astrophysicist, a routine day in the life for someone like you, it would be great to start off with.
Yeah, sure. Firstly, I think it's good to see everybody, although I don't get to see the videos, I see the pictures of somebody. So that's actually very nice, and hope everybody's doing safe. So what does every day in my life look like? So I guess I'd like to first say that pursuing some pure science field like astrophysics can be very exciting and rewarding. Um, so typically as an astrophysicist, you're either affiliated with some university or in some national labs, at least in the US. And regardless of which university or which lab you're working on, I think there are some aspects that are pretty common. So typically, we all have coffee together in the morning and discuss the recent papers, some of the recent papers that have just come in. Nowadays, we don't get to meet for coffee, but we still have Zoom sessions talking about some of the interesting papers. And contradictory to what many of you might be thinking, astronomers don't look through the telescopes anymore. Most of our data comes in the form of images, digital images, which also means that most of the time we are just programming, trying to analyze the images, try to make sense out of the data that comes through. There is also a lot of technical aspects involved on top of science pursuits. For example, like I said, there is a lot of programming. So a lot of computer science knowledge is also used in everyday life. Sometimes on some of the days, I've definitely felt like, am I even a scientist or I'm just a programmer? But that's just part of it. It is the satisfaction that you're working towards something that is pure and noble. I think that's the exciting part.
Wow, wonderful. Although you're not using telescopes now, astrophysics for me is something that's placed at a very high level. I'm sure you require a lot of computational power to work with the data that's coming across. So how exactly are you coping up with work from home in terms of your research, since COVID-19 situation has forced everyone to stay indoors and carry out their work life?
So in a way, we are fortunate because most of work has which we can't even from home, and a lot of my meetings have involved remote participants even pre-COVID-19 days. So we are still used to this kind of setup. I think what is for some astronomers, this is not the case because there are some new telescope sites under construction which have stopped because they are hardware jobs which require a lot of people to be physically present close together. So they have stopped that. A lot of observatories have also stopped collecting data because you also need some expert to be at the telescope site, handling the telescope, which we are not doing anymore. So there is no new data coming in, but we have enough data that most of us could work with on a software front. And on a personal front, I think this is the hardest hit are people with kids, and if they have to look after the kids, teach them because they're not going to school anymore, that takes up a lot of time from their work life. So that is, but that's something that is common to everyone and not just astrophysics. But otherwise, I would say we are fortunate that our work is not affected so much.
Oh, wonderful. And since you're talking a lot about data, it just gets me curious, because what I have in mind when it comes to data analytics is just Excel spreadsheets, but you're working with high resolution images. So could you brief us about how big data is connected with astrophysics?
Yes, sure. So astronomy is actually a very excellent source of big data. So for an example, let me talk about the project that I'm working on, which is called as LSST, which now stands for Legacy Survey of Space and Time. So this is a telescope or a project under construction, which is expected to start collecting data in 2022. And when it starts operations, this will be generating about 1 terabytes of raw data every night. And it will do so every night for 10 years. So at the end of this 10-year project, there will be like about half exabytes of data. And I'm pretty sure you might have not even heard of exabytes. Like it's terabytes, petabytes, and then exabytes. So that's the amount of raw data that is going to be coming in. And there are dedicated optical fibers that are laid under the ocean to transfer all this data from Chile, which is where the telescope is, to Illinois, which is a state in the US. That's where Chicago is. So the data has to be transferred from South America to North America and then stored in a supercomputing data center, which is where the data is processed. So you can imagine the amount of data coming in. And this is the image data which we will process and then release it in a tabular format something like what you see in Excel or in Pandas. And this is not even the most data intensive project. Currently there are so much data in a slightly different set of telescopes called as radio telescopes. They generate about 1 petabyte of data every night, which is 1,000 times more than what my project would generate. And which means there is no way to even store every possible observation. So you even have supercomputers at the location of the telescope as opposed to having in a different continent, which has to do all the processing real time, reduce the data to just the quantities that you're interested in and throw away data. And if you're throwing away data, then you have to think really hard about what you need to have, what you have to throw out well before you can start analyzing the data, because once you throw away the data, then there's no way of getting back. So astronomy has been in this cutting edge when it comes to big data, thinking hard about what is the best way to handle data and process data. And it's actually very exciting even from a data science perspective.
Yeah, and honestly, I'm just throwing this question because I'm really curious. Since you're dealing with terabytes and terabytes of data, are these data consistent enough for you to carry out your research, or do you have to prepare it to a particular structure in order to do that?
Sometimes we have to reorganize the data. So that's why I also differentiate between raw data and some processed data. The raw data, if you look at it, it'll be like junk. You will not be able to make sense out of it in any way. Then there is a separate calibration procedure where you have to take fake data, in the sense you will close the telescope and then try to observe just to see what artifacts the telescope itself is introducing, and then you have to process them together and then make it into more usable format. And images also have to be reduced to a tabular format that you can then load and do some statistics.
Wow. Wait, and I had the. Are you done, sir, or am I?
Yes.
Yeah, okay. No. I had the pleasure of visiting your GitHub page, and I noticed that there is an entirely separate module that you've programmed for galaxy stimulation. And actually, even while looking at your profile, it was a bit confusing for me because it had a diverse amount of skill sets and fields that you worked in, which, to be frank, it was very inhuman for me. And there were several other programming languages which you work in. So what really developed your passion towards programming?
So yes, as a scientist, you just cannot get away from programming. So initially when I started, I think I was just passionate about science or physics in general, not about programming. But soon I realized, okay, doing physics or science is not just the pen and paper kind of calculations that we do in high school or even in the early college days. The real physics really happens only when you program and do the calculations on a computer. There is no way you can do this in the pen and paper. So to begin with, your programming was just a necessary tool. And then once I get used to it, then I started to appreciate programming aspects more and more. So having said that, yeah, you will at least need some kind of basic Python scripting if you have to do serious science. And GALSIM just happens to be one of the projects that me and my PhD advisor were working on. So if you remember, I said like sometimes you also need to have this kind of fake data sets for calibration purposes. And so for a project like LSST that I'm working on, which is not in operations, which means we don't have the data, but we are developing the software and algorithms to process the data when the data comes in. So we are just developing software without any data, which means there is no real data to test on. So we need some kind of a test data set that would mimic the data that we will be getting. And GALSIM, which stands for Galaxy Simulator, essentially simulates the images of galaxies, the distant galaxies that we will be observing in a similar way. So there will be artifacts that would be introduced by telescope, there would be noise that would be inherent in the data. So this GALSIM is intended to simulate all those problematic or problem-causing elements and to see how well we are able to handle this. So it is the other aspect, or in a sense, it is the test case for a software development, I would say.
Wow, that's wonderful. And we can surely understand the importance of programming, because even in Raj Lakshmi Institute of Technology, we have students from various different majors working on programming. It's almost like a necessity for us. And I noticed that you did your undergraduation majoring at electrical engineering, and from there you took a complete shift into astrophysics. So I was just curious as to how electrical engineering is helping you out in your present role, or is there any correlation between astrophysics and electrical engineering?
So there is actually a very direct connection that I see between electrical and electronics engineering and astrophysics. So in my day-to-day job, I do a lot of image processing of the astronomical images. And I still use concepts that I learned in my undergrad. So I still use Fourier transformations, and I use concepts that I learned in my signal processing course. And I said the images are captured in CCD devices, and we are looking at so much precision and accuracy that we need to know the inherent workings of those CCD devices. So what I learned in my solid state physics course still is helpful. And the connection between electronics and radio astronomy is even more stronger, because you have to deal with circuits that process these radio signals immediately. You have to understand the physics of electromagnetic radiation and so forth. So the way I see it, astrophysics has to be a very specialization within the broad electrical engineering. And I also want to generalize and say that this is not just electrical engineering. A lot of engineering fields will have an application in astrophysics. I see astrophysics as a place where all sub-branches of physics and pretty much all branches of engineering can also come together. So just to give another example, since you yourself are a mechanical engineering student, I can say that your experience in, say, fluid dynamics could also help in astrophysics, because there's a lot of simulations about how gases and fluids in general have to interact, how they will heat up and form stars and so on. And that is something that you could apply and that you could use in astrophysics, just as an example.
Great. And wow, that's a whole lot of opportunities opened up for engineering then. And although it might seem like there's a lot of cohesion, it was kind of a leapfrog jump that you took towards an entirely different path. And I just wanted to know if there are any risks associated with switching your field of career from your field of study, because around 80% of undergraduate students don't really go into the field of study that they did do in college. So the risks associated with it and the kind of considerations a student is supposed to take in order to do that.
So there are some risks involved whenever you think about changing fields, but that does not mean you should shy away from doing so. So sometimes you will just have to find how your current expertise links to some small aspect in the new field. And once you make a switch, then you can find around a way to do something completely different. For example, like I said, like I could have just started with some image processing, which I still do, and then move on to something probably nothing related to electrical engineering. So I think if you're switching fields, you need to find that link. And to also build credibility, it would be best if you could show that you've done some work. For example, a lot of astronomical data projects are also up on Kaggle. So if you've not heard, Kaggle is this website where you can go in and contribute code, and like you can run your code, you can compete with other people in analyzing data. So there are lots of astronomy projects in Kaggle, and that if you have something to show, that will also serve as an evidence to say that you're really serious about it and you're not just shifting fields because somehow you are not able to perform well in your previous field or other things. And especially since you're all undergraduates, I don't think just your 4 years of undergraduate study, your department should already confine you and define you, say, oh, you are a mechanical engineer, you are a civil engineer. You're still very early in your career, and there is a lot of opportunities for you to explore other fields.
Well, I think we have to have a diverse mind to approach things like that. And but is this something that you planned out before joining your undergraduation, that you were going to do your post-graduation in astrophysics, or is there some life event that happened which propelled your interest towards this field?
So I was in physics even when I was in school. But then when I joined college, everybody told me it's still a risky thing to take physics as your major and not a more practical field like engineering. So I listened, and then I took electrical engineering. But then after like some 2 or 3 years, I felt like, okay, I've done a basic degree in engineering. If nothing, I can always fall back to it. So I thought now is the time to actually take some risk and try out the things that I really like. So I then applied for a graduate program in physics. So this was master's and PhD combined. So this was in general in physics different, but since you're asking about particularly astronomy, that was more of an accident, because when I was looking for what projects I could be working on, there was a new professor in cosmology, which I ended up working with, who was looking for students, and I was looking for projects. So I thought, okay, let me try this out. This is something new for me. I can see how this works out. And once I joined my advisor and started working, I really liked the field. And I began to see that, oh, this has applications from all fields, which is pretty cool. So I just continued working on this. I would say it's more of an accident, but the physics itself is something that I really wanted to work on and was passionate about since high school.
I can certainly agree on that, because I do have a love for physics, and that's why I took mechanical engineering. Can you tell us more about your experience with Indian Institute of Technology and how it helped you shape your career in future?
So my 4 years at IIT Madras gave me a chance to explore different options. So although I was interested in physics, there was some time where I tried to get more into robotics or trying to see if I would be happy with some subfield, some specialization in electrical engineering itself. What was particularly nice about the undergraduate IIT Madras is they also had a minor option where I could take courses from another department. And to see how much I like physics, I took a minor course in physics. And once again, I started appreciating how much I like physics over other subjects. So, and the there was also a very friendly interdepartmental nature, which means I also got to do more courses in physics than whatever was required for a minor. So I swapped some advanced engineering courses for advanced physics courses. My final year thesis project was also in physics, although my degree is in electrical engineering. So this interdepartment friendly nature helped me really in choosing my career path the way I wanted, and the professors there were also very helpful and encouraging, and I think this all played an important role in what I am today.
Definitely. The interdepartment culture is something that we don't see in a lot of institutions throughout India. And how important do you think that is for all of us, or every university, to implement such a structure to academics?
So I think the segregation between departments is something that is getting little old now, because all the new jobs that are coming are fairly interdepartmental. They require expertise from two or more fields. So while it is good to focus, on one particular subject as a core thing or one particular field, you still need to know some basic ideas from pretty much every other field, so that you know where you can get ideas from, and an interaction across departments is something that will enable this kind of this knowledge transfer or sharing of knowledge and ideas.
Definitely.
And that's something that US universities are actually getting more and more involved in, and they're active about this. Yeah, and I really wish to see this more in India as well.
Yeah, I was getting to that point where, when I first took a look at your profile, there were various different universities that you were associated with, and majority of them were very familiar to me because they're the top universities towards the western side of the hemisphere. And how different is the academic approach in these Ivy League colleges like Princeton University or the University of Toronto different from its Indian counterpart?
So let me first talk about the US universities in general, or actually I could also include some European universities, and then talk about the Ivy League, because some aspects are common across all US universities that I would want to differentiate from the Indian universities. So yes, here there is a lot more emphasis on all-rounder personality. So in fact, the universities here don't even expect you to pick your major department, saying mechanical or electrical engineering, pretty much until the end of second year, I think. Also, that's a fair warning. I have also been in different universities at different stages, so I probably will not be able to do a very fair comparison, since I was an undergraduate in Indian University and master's in the US, so I can't really speak for the undergrads in the US. From what my understanding and interacting with the undergraduate students, it is that you also get to pick two different things and pick a lot of courses, so that you can still see what is interesting you in your first few years of undergraduate. So there is also emphasis on subjects that are not emphasized in India, for example, in like arts and history and philosophy. And I'm still talking about universities that are more science and technology oriented. Like Carnegie Mellon University, uh, for example, it's well known for computer science and robotics, but I don't think any of you would know that it is also has the most famous drama school, um, because they also emphasize on these kinds of arts and humanitarian aspects. Um, there is also in general a lot of preference towards sports, so they also hire uh, students who are good at sports because they can represent their colleges in different sports events, different leagues. And that also means that you have this diverse set of students who you interact with, which broadens your horizon in your 4 years of study. So I think that's something that is very different. And as far as Ivy League is concerned, I think the main or what is making Ivy League so famous and good is the strong alumni network that they have. So even if you've not directly interacted with somebody, if you know that they're from the same university, then you take extra care and put in extra effort to help them out in their career and whatsoever. So they have this strong network. They come back to the universities. They interact with junior students. They also help the university itself in general, and that is building this very nice brand for themselves, which is also why I think they're famous.
Wow, great. And what about the student culture? I hear that there's a very limited amount of time that students actually spend in classes that in universities in the US, and they spend a lot more time interacting with each other in the campus and working on research papers together. So how does that work? Could you brief us something about that?
Yes, so the classes, yes. So there is some learning that happens in classes, but a lot of learning also happens from your peers through those interactions. So if I have to give an example, so if you're working on some projects together, say this could be people from different backgrounds, which means they also have different expertise, different knowledge. And when you work on a project together, then you just learn from each other than learning from a single teacher in class. And that does help a lot. But that also means that different people learn different things. And once again, at a later project, if they come together, then there is so much more to learn always, rather than having a single source of wisdom.
I think I've almost exhausted the list of questions, and I just wanted to ask you if there were any defining moments in your life that you could share with us.
It's hard to pinpoint a moment, but I'd say a defining phase was my 4 years of undergraduate at IIT Madras, because this was one place where I also came across people from different backgrounds with different sets of skills and knowledge. So as a child, I think I was very egoistic, and I would want to win every games and always be the topper when I was in high school. And in this 4 years, somewhere I think I became more humble. I didn't really care about losing. I saw losing as a part of life. I didn't want to be the smartest person. I was happy to be a dumb person among other smarter people. And I think that changed my life and perspective in a way. So that also means that I was not hesitant to try out new things where I would fail. And that also enables me to take risks in terms of career moves or in terms of ambitious projects that I want to do. So I think that phase, I would say, was had an important role in defining who I am today.
Great. And I think we've come to an end point to this webinar, and I'm not sure of the count of the participants here, but most of them are students from our institution, and if there's any kind of advice that you'd like to give to them, you could.
Yeah, so I guess my advice will probably be also on a more academic front, since I've always been in academia with universities. So depending on what you see yourself in life, this may or may not be applicable. But regardless of what you're doing in life, I guess there will always be some kind of learning component. And just like compound interest in savings in banks, it also is applicable for learning. So what I realized, perhaps a little late in my life, is that learning is also like compound interest. The more you know, the faster you can learn more things. So if you can learn something today rather than like a month later, learn today, because that also forms as the basis from which you can connect new ideas better and in general grow your knowledge faster. And because you learn more things if you already know things, it would also be best to find what interests you, find your passion as early as possible. But again, that does not preclude you from being stuck with whatever fields that you have chosen currently. You're still early in your career, early in your life, and if you're not happy, if you're not passionate about what you're doing currently, you can always change. But whenever you do so, be fast in learning new things so that you can learn more things faster. I think that would be my advice.
Wow, thank you so much. And I personally have to tell you that I enjoyed this interaction with you. And thank you so much for answering all my inquisitive questions. But it's not over yet. We have some amazing questions coming from the crowd, but I don't think I've taken a note of that. Can I transfer the mic to Anand sir? Could you please come in?
Yeah, hello. Am I audible?
Yes.
Yes,
sir. I'll just read out certain questions that have been typed by our participants. Actually, the first question is somewhat an interesting question. So it's about UFOs. I think in the news, I think there was some recent event saying a video of a UFO has been released, and even Pentagon was talking something about it. So what do you think is the veracity of that claim? Is it really an UFO?
So talks about UFOs have been there for like few decades now. But somehow there has never been a very credible source for them. So I don't know. I mean, I have personally never seen one, and I don't know how much to trust the sources that talk about UFOs. So I am of the belief that they probably don't exist. I mean, they're certainly not aliens, if that is what you're hoping to hear.
But do you think
they could? Yeah, sorry. Go ahead.
Yeah, please.
No, so they could be some kind of like an artifact or some. They could even be like just an aircraft or something. But I have no idea what they are, and I don't trust them.
But there have been a lot of science fiction movies. Do you think alien life form is there? I mean, it's a common question asked anybody associated with space. So what do you think?
So there is definitely possibilities of them existing. We just don't know of any alien life, but just probabilistically speaking, I think there has to be life somewhere else also in the universe, maybe very far away that we can probably never imagine even coming in contact with them. It is just that we don't know if they exist or not for sure.
And we have a question. Quantum computing and astronomy. So what is the scope of quantum computing in astronomy as of now?
So as of now, quantum computing is just getting realistic in the sense that it's moving from a theory realm to having real physical quantum computers with a few qubits. But it is still far away from using quantum computers in a large-scale applications for any useful purposes. So what is really powerful or doable with quantum computing is that problems that are hard to solve computationally. So you might have heard about like NP-complete problems and so on. And there are certain classes of problems that are difficult to solve using the normal computers, or what we call as classical computers. And there are special algorithms that make solving those problems possible in quantum computing. But as far as I know, astronomy does not have those kind of problems where, by that I mean, it's not the case where we have a class of problems or a problem where it is just hard to solve computationally. I think we are at the state where we have to understand what the data is telling, or understanding some systematic effects in data which we have to eliminate. And also what is a good application for quantum computing is solving problems where you can verify answers if they are correct or not. So one of the classical problems that you can solve with quantum computing is factorization. If I give you two large numbers, it is easy to multiply them. But given a very large number, it is difficult to factorize them. So the classical case is this factorization that quantum computing solves, because a classical computer takes forever to solve this problem. It's one of those hard problems. And quantum computing is inherently probabilistic, meaning that it will give you an answer, but it may only be correct with a 50% probability. So that means you cannot be sure that the answer is correct. But this factorization is this class of problems where you can check if the answer is correct or not easily. You can do this on your calculator or on your laptop. So if a quantum computer gives an incorrect answer, which you can verify, then you just ask it to do this computation again and hope that it will give you the right answer the next time. But astronomy does not have those kind of privileges where it is easy to check an answer. So I don't think there is scope for application of quantum computing in astronomy. I might be wrong, but I just don't know of any such things.
Okay, sir. And we have a question from a student. So he has asked, is robotics a good career to pursue? And especially in the field of cosmology. Because in future, if you're going to talk about space travel, I think a robot which can live for a longer time. So it can do a lot of stuff in the other planets.
Yes. So robotics has applications when it comes to projects like Mars rover and so on, where like you send probes to other planets, or even just in outer space. So I would think even building satellites is more robotics than anything else. So yes, I would say robotics has scope in astronomy, but it is also, of course, more general than astronomy. So I guess where most of the robotics research is going towards is in self-driving cars, and a lot of companies are investing in that. So even just so although it may not sound like robotics, just determining which objects are obstacles, which objects are somewhere in the background, how do you have to navigate through these obstacles, that also comes under robotics. And if I think personally that is where the career options are brightest in the current scenario. Of course, this can change anytime soon.
Okay, thank you. And we have a question from, I think, a researcher in deep machine learning. So he is asking, is there any resources to access cleaned space data sets or any online AI tool to work with tailored space data sets?
Is this relevant? Is this in the context of astronomy or?
Yes, especially, yeah, if you, I mean, people are using a lot of images and other data to train their models, deep learning models.
Yes.
So if somebody is looking for creating an application, for example, I need to spot a star or something like that. Is there any data sets available which can be used by our people to use in a tool like MATLAB or Python?
Yes, there are actually a lot of public data available in astronomy. If you don't want to do any programming but just look at the data, there are several projects in Galaxy Zoo. This is also beyond astronomy, where you just have to look at the images and then answer some questions about the images, which is then and your responses then become like a new data trying to describe the images. So it gives a human element to it. But if you also want to do a more programmatic approach with the data, there are several tables that you can download from. If you just Google for YZ, or let me just type this on chat. So this YZR is a repository of a lot of catalogs or like tabled data which you can download and analyze yourselves. You can also find images on ESO, which is European Southern Observatory, and even you can also view images taken from Hubble Space Telescope. I think it's on the NASA website. So a lot of data is public, and if you want some guidance in starting to analyze these astronomical data sets, and if you want to learn how to start, there is a course in Coursera that I found really helpful. It's called Data Driven Astronomy. It's from University of Sydney, where there's a lot of emphasis on also programming and analyzing the data as a part of those assignments. And I think I personally use that to also explore subfields of astrophysics that I am not actively researching on. So I would strongly recommend that particular course for everybody if you do some programmatic aspects of astronomy.
And we have another interesting question. With your experience in cosmology, how will you connect astronomy and astrology to the life of events of a person?
Astronomy is, okay, I might come strong opinionated. Astronomy is a science. It just deals with what are the objects outside there, stars, galaxies, comets, asteroids, and so on. Astrology charts is not science, it's pseudoscience. It charts the movements of planets correctly, but there is no evidence that it can affect lives of a person. And they have done blind tests to see if astrological predictions have any statistical significance in predicting life events. Of course, sometimes you can get correct by fluke, but there is no statistical evidence that you can predict events accurately. So no, there is no connection between them.
Okay, sir. And can you give some insight on the research methodology? If there are new researchers, how should they start?
So I mean, I think it also depends on what kind of projects that you want to get involved in. So if you can find a research advisor who can guide you through this process, I think a research mentor is definitely required, especially if you're new to research and you've not done before, because you still need to be handheld in how to think about data, like what are the pitfalls that you could fall into. Unfortunately, I don't think there is any online course for research itself. You would need somebody with personal interaction. But if you just want to like get started into looking at data sets, then the Coursera course that I suggested is a good resource to start with. And there are also some, so typically many universities have some kind of an undergraduate research program or a visiting research program, which you could consider applying to. They will also be fully funded, but they will want to see that you're serious about and doing some of these online projects might help in that aspect.
Thank you, sir. And there is another question. So actually, they asked which is more accurate, that is deep learning or quantum computing. I think quantum computing, if my understanding is correct, it has to do with the hardware, more like, that is, we start from the atomic level. I think what is quantum computing? I think we already answered the question, but there might be some people who have no idea about what is quantum computing.
So quantum computing is essential. So in classical computing, you have, the information is encoded in two states, which are just called as 0 and 1. The numbers themselves don't have meanings. What is fundamentally different in quantum computing is that you have objects that are equivalent to transistors, which will not just be in one or the other state, but it can also be what is called as the superposition of both the states, which means you can encode information you're encoding information in a very different manner. If I want to say that question kind of caught me off guard. So I have some experience in quantum computing, but I was prepared to talk more about astronomy. But anyway, I'll try to answer this question. So,
it was from a student actually.
Yes. Yeah.
Usually they catch us off guard most of the time.
Sorry?
Usually they catch us off guard with the questions most of the time.
Yes. No, that's fine. So this fact that you can have objects in multiple states at the same time enables you to come up with algorithms that are fundamentally different from what you can run on classical computers, which make this assumption that you have one or the other state. So by having these atomic objects, or what is called as qubits, in multiple states at the same time, the interaction between them is also getting more and more complex, which means the dimensionality of this system is much larger than what you will be able to what you can have classically. And this large dimensionality of your data also allows you to encode objects more efficiently. But ultimately what happens is, when you still make a measurement, you're going to get one answer, or one answer for like every qubit. But the processing itself happens in a very large dimensional data, in large dimensional space. So a lot of computation, if you devise your algorithms cleverly, a lot of computation that cannot happen in a classical computer easily will happen in this large dimensional quantum space. And then it'll still give you an answer that is probabilistically correct. So I think the question was on also deep learning and quantum computing. Deep learning is...
Which is more accurate?
I mean, yeah, it is more of a building a complex model just to describe your data, and they're still fundamentally different things. One is more about using the properties of physics to come up with different class of algorithms to solve a problem, and deep learning is coming up with more complex model that can describe any sort of data without making any strong assumptions about it. But there's also research in combining the two, because deep learning typically requires a lot of computations. The training that you need to fit the data or to describe the data is enormous. And there is research in seeing how quantum computing could accelerate this learning process in trying to fit a deep learning model to the data. But there's still two different things which you can combine to make a powerful tool, but they're not something that you can compare by themselves.
Okay, sir. And sir, last year we took a picture of black hole in the space.
Mm-hmm.
So what is its significance?
So I think this was the first direct evidence that we had that black holes exist, because I think because at some point I would say maybe like 50 years ago, it wasn't even clear if black holes existed or not. It was possible theoretically, but there was no evidence. And then sometime around 1970s, there was an indirect evidence for black holes saying, okay, there are stars or other things that are revolving around that are going in circles around nothing, or what looks as nothing. And so there was this hypothesis that, okay, those could be the black holes, and there was like an indirect evidence. This image of black hole was a more direct evidence to see that this is exactly how we thought it should be. So you can't see the black hole itself, you just see it as a black spot. You just know that this exists because of this, what we call as accretion disk, or materials falling into the black hole, and in the process of falling they get very heated up. So this is similar to how meteors falling from space onto Earth get heated up. There's lots of friction and they get heated up, and then they emit light, and that is what you are seeing. This is exciting scientifically in that you're seeing an image of a black hole, and it's also exciting technologically because this is an unprecedented level of resolution that you have to achieve. This is looking like at a small strand of hair placed on the surface of moon, and trying to detect that strand of hair on from the Earth. So the level of resolution that you need to actually pinpoint this and identify required a telescope whose diameter was as large as the Earth itself. And that is what this project did by having radio antennas at different parts of the world and then combining. And I also mentioned that typically such radio observatories need to have supercomputers locally, and they will be discarding a lot of data. So if you have these worldwide array of radio antennas and you have to discard data, then it was a technological challenge to how to bring all the data together at one place so you can combine the data and then make this image. And I think that was the challenging aspect which they did brilliantly in this by the Event Horizon Telescope team. So I think this is a very great job on their part.
Yes, sir. Yes, sir. So I think we have a couple of more questions. So I think we'll go for the last question now. And the remaining questions, it will be directed to our guest through email, and the answers will be forwarded to you directly. So due to shortage of time, we are finishing with the last question. So we have a question from Chandrasekhar. So what will be the role of industry's environment to protect the cosmos?
I'm not sure I understand the question fully, but I can answer a related one. So one of the challenges that we are facing that my project is facing now is that there are companies that are launching low orbit satellites into the Earth. So this is more for providing internet to African countries or regions which do not have this infrastructure um, to have vast internet coverage. And while that is good and it's practically helpful thing, what this would also means that you will have thousands of objects eventually, or thousands of star-like objects that are going around the sky, um, which will firstly enable the night sky for every average person, because you can no longer look at the same stars. You will be seeing stars, star-like objects that move, and this is also hindering astronomy, because if you're trying to study stars and then these bright star-like artificial objects will actually damage the whole observations, rendering most of the data that we collect useless. Of course, this is not an argument to say that those poor countries in Africa should not get internet coverage, but we are actually working with them to see how they can still achieve their goal without trying to ruin the night sky for everyone. And this is still something in discussion. So this is, so just to say, one example is Starlink, which is run by Elon Musk, and they have actually been very receptive to us. Some of our project leads are talking to Elon Musk, and we're trying to figure out what is the best way to solve this. I don't know if that is what Mr. Chandrasekhar intended, but this is how I understood the question and I'm answering.
Yeah.
Yes.
Okay, sir. I think we have come to the end of the very enlightening session, and the level of technicality, the level of information that was provided during the session, I'm sure that it would inspire many other people to pursue their career, if not directly, at least indirectly, towards astrophysics. And so first I would like to thank you, sir. Thank you very much. As Vinod pointed out, taking everything into account of what's happening all over the world, and of course it's happening more in US. So you have taken your time to join us. So we have 100 plus participants in the even now. So I hope all of them got really valuable points during the session. So I think I give Vinod to thank you also. I think more students benefited from this session. So based on the behalf of the students, I request Vinod to give the vote of thanks and wind up.
Thank you so much, sir. This was truly a very informative session, and in most part of the interview, I actually got into the context, and the way you conveyed the answers for our students too was commendable. And I also like to thank every one of the participants who took part in today's webinar. And I think it's very important that in this time of turmoil, we engage constantly in such social interactions to keep our minds active. And it is a wonderful initiative indeed taken by our management to organize such webinars. And we're going to be seeing a lot more of this. And we hope that we all meet again and participate in such webinars. Thank you so much.
Thank you, sir. Thank you very much.
Thank you. It was my pleasure talking to everybody. Stay safe.